Hello, and welcome back. Today I will be going into more detail about the database and communication systems I introduced in the previous video. Starting with the database, at its core, it is built up of various tables. These tables each reflect a piece of shared data that will be used across various aspects and systems of the game. A table is an interface that wraps an RCU and provides read and write access into the shared resource. The bulk of the persistence work lies inside of the RCU. Traditionally, RCUs are used in kernel space. Because of this, they have the advantage of making the read lock essentially a no-op. RCUs are favored here as they provide real-time performance meeting the requirements of the kernel. However, we work in user space, but this is not necessarily a disadvantage. The read lock will not be able to be boiled down to a no-op since we do not have access to the thread scheduler, but we can use history to our advantage and ensure quiescent states amongst the readers. And again, while we're not working with the kernel, the read-side performance of video games is very similar to that of the kernel, which is the motivation for using the RCU in the first place. There are many models with varying implementation details for the RCU, and the one I will be showing today is developed to hopefully work with the real-time shared data requirements of video games by leveraging low right-side critical section contention and high read throughput on shared memory. Beginning with some design details, for this RCU, readers have been prioritized to have arguably wait-free read access, and writers are given their abilities in a lock-free manner. Readers must be registered to the RCU, and in doing so are given a read index into a synchronization structure, and this synchronization structure is simply a padded boolean, well, padded to the cache line, and that is done to avoid false sharing. This boolean is used to signal to the writer that a current read is being attempted in this generational slot. And as you can see, the read flags here are held in an array of the generational read flags. This is also why we needed the padding. Writers, on the other hand, must do their best to minimize the amount of time spent updating the shared memory. To do this, writers prepare the data beforehand, here in this pointer, and during the synchronization, the writer makes their data visible to future generations by placing it inside of a future generation handle. Like every RCU, the readers and writers must work in agreement with one another. A writer cannot delete a reader's data, and a reader cannot hold a handle to a generation forever, causing the current or future writers to spin in a loop. To try and get an idea for just what the data is doing behind the scenes, I found it easiest to try and visualize the relationship between the data and the reader and the writer. So let's first talk about the reader. The reader is interested in getting, at this very moment, the most current piece of data. And in order to do this, a global generation is used to keep track of the generations in which specific instances of shared data belong to. And it should be noted, only a writer is allowed to increase the generation count. Once the reader has the current generation, a read attempt is made on the current generation by setting the reading flag that is reserved for the reader to true. The reader then performs double-check locking to ensure that there wasn't a write that took place in between the read load and the store of what is now the old generation's read flag. If there was an inconsistent state detected, this means that the reader must make a new read attempt as shown here in step 3. In order to keep the previous writer locked out and unable to advance any other potential writers, the current generation is first locked and then the previous generation is unlocked. And this is actually where the comment of readers being arguably wait-free comes from. In this example, max generations is set to 2. This is because only one writer is allowed at any given time. Should this be upheld, then the reader will always be able to complete their read request in a finite number of steps, though it may vary between request to request depending on if there was a write. Currently in the code, a while loop is still used, as in the future there may be cause for allowing multiple writers at any time, and forgetting about this change to an if statement may cause developmental nightmares. However, I do fully suspect the single writer requirement to stick, and because of this feel confident in making the statement that the reader is wait-free. Moving back to the read lock part of the algorithm, once the double check locking is passed, we have a guarantee on the lifetime of the resource that is returned in the handle in step 4. Once we finish our read on the data, the handle is returned using the unlock function, where the flag is removed and any writer waiting on this reader is now free to reclaim that memory. And the actual specifics for that code is right here. So we first do a load, and this is relaxed because we don't really care what it is. We just want to get the current generation as fast as possible because we're still going to do a double check. And when we do that double check, then we can use memory barriers. The next thing we're going to do is we're going to get the generation index. Now, I've simply just used and here because 2 is a power of 2. And ideally, you'll want to, if you're going to use multiple writers at a time and have multiple buckets that you need to worry about, use a power of 2. Modulo, I mean, I have modulos all throughout the code base. They're just slow. We want this to be as fast as we can. So let's use a power of 2 and an and. From there, we are going to make that read attempt, and we are going to use a release barrier here, and it'll make more sense when you see the write code, but it is paired, I believe it's paired within our quire. We just store old generation. Now here's that while that really can be changed to an if statement, but essentially while we can't guarantee the double check lock, we want to say we're making a new read attempt on this generation, and now you can go ahead and get rid of the read attempt on this old generation. This is using a release because, again, when the writer is trying to synchronize, we need some guarantee of the ordering. But the relaxed here doesn't truly matter because when we, sorry, I had to go look at the code just to make sure. When we are going to release it, we don't necessarily care about when this false gets there, right? It can get there before the writer attempts to do the read, or it can get there after the writer attempts to do the read. We're not using that slot of memory, so it doesn't really matter in our case from the reader perspective. And then when we finish, we return a generation handle, and this is the definition. So it's just it copies over the pointer and the generation. The generation is then used in the unlock to generate the index, and then we simply do again a relaxed release of the false, or sorry, a relaxed store of the false. Now we can move on to the responsibilities of the writer. In step 1, the writer first loads the current generation and calculates the index of the generation, which will be made old. Then in step 2, the writer calculates the next generation as well as its index. The writer also prepares a new handle for this generation of data as well. Moving on to step 3, the new generation index is used by the writer to publish the handle for future readers and then stores the calculated new generation as the new global generation. By doing this, the writer ensures that all their updates are visible before any visitors arrive to view it. The reader then begins a wait loop that spins until all readers are finished with the old generation as seen here in step 4. This is ensured by starting with the first registered reader and checking if their reading flag for the old slot is true. If so, then the writer will wait for this reader to finish. The writer then repeats this for each reader until there are no more registered readers to check. By using some ordering in the checks, once a reader has reached 0, we can safely guarantee that reader will never read that generation again since it is now old. Once we can make this guarantee for every registered reader, we call the deleter for the shared resource, reclaiming the memory and ending the fifth and final step. And now, as with the readers, I will look at the code for the writers. And we can see we begin by getting the old generation and then calculating that index. And I previously explained the modular versus and. Then we prepare the new generation for future readers by setting up that handle, which will eventually be written to using the new generation's index. And then we perform a store of the global generation using our newly calculated generation. And this we use the release, which is paired with this acquire up here. Once we have made that visible, no future readers can see any of the information that is stored in the old handle, or the generation handles using the old index. So we begin the wait loop to simply wait for each of the registered readers. Then while they're reading, we just acquire that flag and we put in a pause. Simply, there's really no point in just always hitting that. If they're reading it, they're probably going to be reading it for a few more cycles. So just take a little break. And this here is just for debug purposes. After we have broken out of this for loop, we know that it is safe to go ahead and call the supplied deleter and the signature to go ahead and clean up that specific memory. Now I'm going to go over the wrapper for the RCU, the runtime tables. I believe in the last video I went over the signatures for the read and write functions, but I did not explain the design as to why. Earlier I said one of the ways to keep the critical write section contention low was to prepare that data beforehand. One of the most common ways of doing this is to use a pointer into the prepared memory, and you can make that pointer visible with one atomic operation. Because of this, the write function signature forces writers of the database table to make sure they are supplying a pointer to their data which they wish readers to use. However, just this requirement alone is too rigid, so the inclusion of variadic parameters is provided so that a true RCU protocol can be performed if needed. The states table I showed in the previous video is actually an example of not needing the full RCU protocol. There was really no need for a read copy, just an update. However, in preparation for this, I actually ported over the terrain code to now work with the database, and in doing so, the opportunity for a true RCU protocol to be performed is now possible. At the moment, the terrain is static, which unfortunately goes against everything I'm about to say, but for dynamic terrain, like that which is planned, chunk loading and unloading becomes a very serious problem. For the RCU, a function handling this may need to pass in additional objects for determining if it needs to perform a particular part of its write or not. It is for those kinds of considerations that the the variadic parameters are required in ensuring full RCU support. Hopping back over to the tables, the read and read copy function signatures have a similar situation. Whereas the write function expects a pointer to the memory for publishing, the read function expects to receive a lifetime guaranteed handle into its data that it's reading. However, just like the writers, this is too rigid a definition to make use of the read data, so the inclusion of variadic parameters are allowed to work with the read data. The read copy function is used in places where holding the data will be too detrimental and is preferable to copy it, but this should be done with testing, as for what I'm about to say. This is actually what I showed being used in the previous video for the node state table. However, I did some reflecting on the code, and I figured that the actual reads and writes being performed come nowhere near that of the potential throughput of the tables. So because of this, I decided to explore the route of changing the state table, or reading the state table, to work with the read function signature instead of the read copy function signature. And while the writer does now incur some waiting, the writer itself does not really appear to be greatly inhibited. For the simulation thread, for example, is not really slowing down. It's losing a handful of cycles. The reader also is now avoiding what would be a very expensive copy when rendering a scene on the scale of a true runtime environment. So now I'm going to go ahead and run the code, and what I'm looking to show is the actual impact of making a choice to extend read times. Now this is release mode, by the way, as debug mode does incur quite a bit of waiting, but I imagine this is because of all the overhead placed on memory in debug mode. In an ideal scenario, you would have close to only reads, as the efficiency of an RCU depends on the ratio of writes to reads. More writes will cause a decline in your read throughput. Specifically in the case of the state table, the default is a simulation of 75 Hz and a render rate of 144 Hz. This works out to a roughly 1 to 2 write to read ratio, which is quite honestly pretty high. You would like many more reads than that. However, the overall time spent waiting is relatively infrequent if you consider the length of actual frame, the amount of time between waits, and then the actual length of the wait itself, as seen in the wait count that's being printed. Now, of course, under the load of a real-time environment, things aren't always so simple, so as always, measure. But with that being said, the RCU itself is fairly resilient to different ratios of reads to writes. As I said before, this is roughly a 1 to 2 ratio, which you're seeing now. If I uncap the renderer, it runs at roughly 4K FPS with the screen capture, which is about a 1 to 53 ratio. And at times it actually looks like it gets off the writer's toes because of how infrequently the two are actually in the table together. And I'll go ahead and do that now. Now, one thing that should be mentioned, and this was perfect that it happened there, was the wait times do seem to have the possibility to be more dramatic. So they are a bit more infrequent with a higher, with a lower write to read ratio, but they do appear to be much more variable. And now for completeness sake, I will actually go ahead and put it to where there is 1 1/4 writes for every read. And all this is just to demonstrate that it's a fairly flexible system for the various types of subsystems that will eventually be worked into the database. However, all of that should take care of the database, its tables, and the RCU for now. The code for the database is on GitHub, and I'll leave a link in the description. However, the individually typed tables themselves are defined from files in another project. And this one has gone on a little long, so I'll be uploading a separate video in tandem with this one that covers the communications model. So thank you, and have a good day, and I will see you in the next video.